Unit Operations Control, Advanced VFD Control for LP process gas compressors. Process gas compressors operating in the low pressure and medium pressure MP ranges play vital roles in refining, petrochemical, and gas processing facilities, moving fuel gases, recycled hydrocarbons, and intermediate products across various unit operations. The adoption of variable frequency drives, VFDs, for controlling these compressors has fundamentally improved flexibility, energy efficiency, surge prevention, and dynamic load handling. In modern industrial contexts, VFD-controlled LPMP compressors are no longer isolated mechanical assets. They are digitally integrated, performance-optimized subsystems within the larger automation and energy management architecture. Traditionally, compressor control relied on mechanical recycle valves and pressure switches, offering limited adaptability during process swings. VFDs have replaced fixed speed drivers and throttle-based flow regulation with real-time RPM control, enabling smooth, precise modulation of gas throughput based on demand. This approach minimizes pressure fluctuations, reduces recirculation losses, and avoids the inefficient energy profiles typical of mechanical throttling, particularly at partial loads. In LPMP applications, where process flows and pressures are more variable, VFDs deliver high responsiveness to both planned set point changes and unplanned transients. At the heart of modern control architectures is a multi-loop strategy involving suction pressure control, discharge pressure regulation, anti-surge protection, and flow balancing. The VFD acts as the primary actuator, modulating compressor speed in response to process variable set points. Suction pressure control is particularly important in LP systems where upstream production, e.g. gas recovery, vent gas, or flash gas, can vary significantly. A PID controller adjusts the VFD speed to maintain suction pressure within limits, absorbing fluctuations without triggering recycle or flare events. Surge control is a top operational priority for dynamic gas compressors. While high-pressure compressors often require dedicated anti-surge systems with fast-acting recycle valves, LPMP compressors can often use VFD modulation alone to maintain safe operating margins. Advanced surge detection algorithms continuously calculate proximity to the surge line based on compressor maps, real-time flow, and differential pressure. When approaching critical regions, the control system reduces speed preemptively, avoiding the mechanical stress and process disruption associated with traditional surge cycling. Process integration often necessitates coordination between multiple compressors, headers, or trains. In such configurations, master-follower VFD arrangements or centralized control strategies balance load across units to ensure efficient capacity utilization. These controllers optimize power distribution, reduce interstage backflow, and allow seamless handover between parallel units. Combined with real-time monitoring of suction header pressure and gas quality, these strategies improve stability and avoid hunting or flow instability at lower pressures. Instrumentation has advanced alongside control logic. High-speed transmitters for pressure, temperature, and flow ensure accurate, fast feedback to the control system. Many facilities are now embedding ultrasonic or Coriolis meters into compressor loops for better mass flow accuracy, especially with variable density gases. These inputs feed into control models that adjust compressor performance in real time, especially important when handling gas mixtures, recycle streams, or light hydrocarbons with varying compressibility. The energy efficiency gains from VFD control are substantial. Since power consumption is roughly proportional to the cube of compressor speed, even small reductions in RPM yield exponential savings. In LPMP services, where compressors may operate far from design conditions for extended periods, VFDs allow operation near the minimum safe speed rather than at a fixed high speed with forced recycling. Real-time power consumption metrics and efficiency curves are now visible to operators via integrated dashboards, often tied into plant-wide energy KPIs or emissions reduction targets. Condition monitoring has also benefited from the integration of VFDs. Built-in diagnostics provide visibility into motor current, voltage imbalance, harmonic distortion, bearing wear indicators, and thermal profiles. When combined with vibration and acoustic monitoring, operators can proactively detect misalignment, mechanical looseness, or impeller damage. This predictive maintenance capability is especially valuable in LP&P compressors, where unexpected shutdowns may not cause catastrophic failure, but still disrupt downstream stability and product quality. Safety and trip logic in VFD-controlled compressors are now more sophisticated. Control systems are integrated with safety instrumented systems (S) and emergency shutdown systems (ESD), enabling tiered responses based on alarm severity. For example, high suction pressure may trigger controlled deceleration, while critical low flow near surge limit can trigger a bypass valve in parallel. Soft shutdown logic protects both process continuity and equipment, reducing risk during utilities failure, load shedding, or unit shutdowns. Digital integration allows compressors to be fully represented in asset models, digital twins, and process optimization layers. Simulation platforms replicate gas behavior under different load cases, supporting offline tuning, startup rehearsal, and operator training. With live integration into APC or MPC layers, the VFD speed set point can be optimized in coordination with upstream production or downstream compression stages. This not only maintains stable operation, but allows compressors to contribute to broader operational objectives, such as energy minimization, emissions compliance, or throughput maximization. Looking forward, AI-driven supervisory systems are being tested for autonomous compressor control. These platforms combine historical performance, live diagnostics, and predictive analytics to adjust VFD parameters dynamically, managing speed, surge margin, and recycle valve action based on anticipated process behavior. In this paradigm, the LP-MP compressor becomes a self-optimizing node within the plant, responding intelligently to shifting production conditions and organizational priorities without requiring constant operator tuning or fixed margins. Unit Operations Control, Smart Crude Oil Tank Gauging and Inventory Management Systems. Crude oil tank gauging and inventory management are foundational to refinery, terminal, and upstream logistics operations, directly impacting custody transfer accuracy, blending optimization, loss control, and commercial compliance. Modern tank farm operations have shifted from manual or semi-automated gauging to fully digital, integrated systems that leverage high-resolution measurement technologies, advanced analytics, and real-time connectivity. These systems are no longer passive recorders of stock levels. They now function as dynamic, intelligent platforms that support operational efficiency, safety, and revenue assurance. Traditional tank gauging methods, such as tape and bob or float and tape systems, are increasingly obsolete due to safety risks, labor intensity, and limited precision. Today's high-performance gauging systems deploy non-contact radar-level sensors, servo gauges, and guided wave radar (GWR) probes that provide continuous high-accuracy measurements of crude oil level, interface, oil water, and free water bottom (FWB). These sensors are typically certified for custody transfer applications per international standards, e.g. API 3.1b, OIML R85, ensuring traceable and legally defensible measurements. In modern facilities, tank gauging systems are integrated with temperature and pressure sensors to calculate volume compensation and convert gross volumes to standard volumes using API 2540 ASTM D1250 volume correction factors. Multi-point temperature sensors are placed along the tank height to capture thermal stratification, while pressure sensors help determine vapor space conditions. This integrated approach enables precise computation of net standard volume (NSV), total observed volume (TOV), and water cut, critical for both operational reconciliation and commercial invoicing. Inventory management platforms consolidate data from all tank instruments and convert it into actionable dashboards and reports. These systems track tank-by-tank fill levels, alert thresholds, ullage capacity, and tank movement histories. They often support tank grouping, blending plans, batch tracking, and automated reconciliation against metering systems or pipeline receipts. Operators can visualize tank status in real time, including alarm conditions, e.g. high level, overfill protection, cooling or heating requirements, and tank heel management, all from centralized human-machine interfaces, HMIs, or cloud portals. Custody transfer and regulatory compliance drive the highest accuracy demands in tank gauging. Modern systems are integrated with flow computers, batch controllers, and terminal automation systems, TAS, to ensure synchronized measurement and transactional integrity. Secure audit trails, timestamped events, and automatic calibration traceability are embedded within the software. These features support internal audits, external regulatory inspections, and dispute resolution in the event of volume discrepancies during crude receipt, transfer, or export. Overfill prevention is a critical safety feature of tank gauging systems. Independent high-level alarms, IHLA, and safety integrity level rated logic controllers provide automatic tank isolation or pump trip commands upon detection of critical thresholds. These systems are often decoupled from the primary gauging sensors to ensure independence and redundancy, and they must comply with international standards like API 2350 or IEC 615111. Some tanks also include radar-based overfill detection sensors mounted at discrete elevations to provide rapid response level detection regardless of tank geometry or turbulence. Data integration with enterprise platforms has expanded the value of tank gauging beyond physical measurement. Tank inventory data feeds into refinery planning systems, terminal management solutions, and enterprise resource planning, ERP tools for real-time logistics, blending optimization, and commercial analytics. API-based middleware enables two-way communication between local tank gauging systems and cloud-based inventory portals, enabling marketers, traders, and planners to visualize tank availability, product grades, and netback scenarios from any location. Digital twins and simulation models are increasingly applied to tank farms. These models simulate tank operations under different temperature, volume, and product mix conditions, allowing operators to anticipate vapor losses, tank wall stress, or stratification risks. Predictive models can also simulate ullage availability during high receipt periods, enabling proactive scheduling of transfers, blends, or tank switchovers, thereby avoiding constraints and demurrage costs. Wireless tank gauging is gaining momentum in remote or brownfield installations, reducing infrastructure costs and deployment time. These systems use secure wireless protocols, e.g. ISA 100, wireless HART, to transmit level, temperature, and alarm data to gateways connected to the control network. Battery-powered or energy harvesting sensors extend deployment options, particularly in harsh or inaccessible environments. These solutions are typically used in conjunction with edge computing units that provide local buffering, diagnostics, and fallback logic in case of network disruptions. As part of the broader digital transformation, AI-enhanced inventory systems are being deployed to perform tank reconciliation, drift detection, and loss detection autonomously. These platforms compare tank data against metering systems, pipeline schedules, and weather conditions, e.g. for vapor loss models, to identify anomalies such as leakage, calibration drift, or unauthorized movements. Combined with video surveillance, access control, and automated sealing systems, modern tank gauging and inventory management has become a tightly integrated solution that ensures transparency, accountability, and operational excellence across the crude oil supply chain. Unit Operations Control, Advanced Catalytic Reformer Control for yield, stability, and hydrogen optimization. Catalytic reforming units are core components of refining operations, tasked with upgrading low-octane naphtha into high-octane reformate and valuable hydrogen-rich gas streams. These units feed directly into gasoline blending and hydrogen balance, making their control critical for both economic and operational efficiency. The control of modern semi-regenerative, cyclic, and continuous catalytic reformers, CCR, involves highly integrated systems managing reaction severity, catalyst stability, product quality, energy efficiency, and safety, all within tight environmental and economic constraints. Historically, reformer control was based on fixed ratios and manual tuning of temperature and pressure. Today, control strategies revolve around reaction severity management, where reactor temperatures, hydrogen partial pressure, and space velocity are continuously optimized to maintain octane targets while minimizing coke formation and catalyst deactivation. Severity is typically expressed as a function of weighted average bed temperature, WABT, which is maintained through cascaded control of furnace outlet temperature and individual reactor inlet temperatures via flow control of hot recycled gas or feed preheat. Modern reformers use multiple fixed-bed reactors with interstage heaters, and each bed's performance must be tightly controlled. Smart thermocouple arrays monitor temperature gradients across each catalyst bed to detect abnormal exotherms or hotspot formation. These measurements are fed into advanced process control APC systems or model predictive control MPC layers that dynamically adjust hydrogen to hydrocarbon H2HC ratios, feed rates, or heater duty to balance conversion and selectivity. When integrated with octane or product analyzers, the system can fine-tune severity in real time to meet reformate quality specs. Hydrogen management is another critical pillar. Reformers produce large volumes of hydrogen that are routed to hydrotreaters, hydrocrackers, or hydrogen networks. Controlling hydrogen purity, recovery, and system pressure is vital to avoid contamination or off-spec downstream performance. VFD-controlled hydrogen compressors, purge gas monitoring, and hydrogen purity analyzers are commonly integrated into the reformer control strategy. APC layers optimize hydrogen recycle rates to maintain catalyst protection while minimizing hydrogen loss to fuel gas or flare. Feed quality variability poses a major challenge to reformer stability. As crude slates become more opportunistic, feed sulfur, aromatics, and paraffin content can swing significantly, impacting catalyst behavior and product octane. Modern control systems incorporate feed characterization models, drawing on real-time naphtha properties, analyzer data, and laboratory feedback to adjust reactor operating conditions or trigger adaptive control recipes. These systems also interface with blending models to ensure reformate volume and octane contribution align with gasoline pool requirements. Energy efficiency is a major focus area in reformer control. Furnace duty, feed preheat, and heat integration via economizers or waste heat boilers must be optimized to minimize energy intensity. Infrared sensors and oxygen trim control systems are used to maximize heater efficiency and detect early signs of burner imbalance or tube fouling. Control systems monitor fuel-to-air ratios and can automatically adjust burner profiles based on load conditions or heat balance targets. Integration with plant-wide energy management systems allows the reformer to operate in harmony with broader utility constraints and emission targets. Catalyst management in continuous catalyst regeneration, CCR reformers introduces unique automation needs. Catalyst circulation rate, coke burn profile, regeneration temperature, and reintroduction timing are all under advanced control. The system must balance deactivation in the reactor with regeneration capacity to maintain stable activity and selectivity. Smart algorithms assess catalyst aging, monitor pressure drop trends, and optimize regenerator conditions, ensuring long-term performance without frequent shutdowns. Safety and reliability in reformers are managed through tight control of pressure relief systems, furnace interlocks, and reactor monitoring. Safety instrumented systems, SSIS, are employed to detect overtemperature, pressure excursions, or loss of hydrogen flow, initiating staged shutdowns or transition to safe operating modes. Alarm rationalization and high-integrity operator interfaces are essential due to the high temperatures and flammable materials involved. Many modern units integrate virtual operator assistants or digital SOPs that guide response actions during startup, transitions, or emergencies. Digital integration has significantly improved visibility and predictive capability. Reformers are now monitored via digital twins that replicate reactor kinetics, heat balances, and catalyst aging in real time. These twins allow offline scenario testing, predictive maintenance planning, and operator training. Combined with AI-based pattern recognition, they help detect early signs of catalyst fouling, reactor instability, or equipment wear. Predictive models can recommend severity adjustments or catalyst regeneration schedules before performance degradation is visible in output quality. Looking forward, reformer control systems are being integrated into refinery-wide optimization platforms. MPC controllers consider not just local reformer economics, but also the value of hydrogen for other units, octane blending economics, and emission credits. As part of autonomous refinery initiatives, self-learning models are being developed to manage reactor heat balances, recycle flows, and purge strategies based on thousands of hours of operational data. These advances ensure that catalytic reformers remain reliable, efficient, and strategically optimized assets at the heart of the modern refinery. Unit Operations Control, Intelligent Fluidized Catalytic Cracker, FCC control for conversion, yield, and unit stability. The Fluidized Catalytic Cracking, FCC unit, is one of the most complex and economically vital operations in a refinery, responsible for converting heavy hydrocarbons into lighter, more valuable products, such as gasoline, olefins, and light cycle oil. Its highly exothermic, dynamic, and interactive nature demands a layered and sophisticated control strategy to ensure product yield optimization, mechanical reliability, energy efficiency, and emissions compliance. Modern FCC control systems integrate advanced instrumentation, predictive models, and plant-wide optimization logic, making FCC units key beneficiaries of digital transformation and autonomous control technologies. At the heart of FCC control is conversion severity management, primarily governed by reactor temperature, catalyst activity, riser residence time, and feed preheat. Reactor temperature, typically in the range of 500 to 550 degrees Celsius, is controlled via the catalyst circulation rate, which is modulated by the spent catalyst standpipe and regenerated catalyst slide valve. Modern slide valve controls are tightly integrated with bed-level monitoring, differential pressure sensors, and position feedback loops. These loops are orchestrated by cascade and model-based controllers that anticipate thermal demand based on feed rate, composition, and desired conversion levels. Regenerator control is equally critical. The regenerator removes coke deposited on the catalyst during cracking through controlled combustion, generating the heat needed to drive the process. Airflow to the regenerator is managed by oxygen trim systems, burner management logic, and high-speed mass flow controllers. In advanced units, two-stage regeneration, dense and dilute phase control is implemented using smart thermocouples, oxygen analyzers, and CO-CO2 ratio monitoring. MPC algorithms balance coke burn, heat generation, and catalyst activity to maintain steady reactor temperature and avoid afterburn or CO breakthrough. Feed rate control in FCC is not simply a function of upstream supply. It is actively balanced with catalyst circulation, air availability, and downstream fractionator capacity. The main fractionator overhead system, which separates cracked vapors into LPG, gasoline, and lighter ends, can become a bottleneck if feed is pushed aggressively. Dynamic APC strategies coordinate riser temperature, stripper steam, and fractionator reflux to align feed rate with fractionation capacity, ensuring optimal operation without flooding or undercutting product recovery. Catalyst management is now an automated and adaptive process. Circulation rates, slide valve positions, and catalyst inventory are monitored and adjusted in real time based on delta P across risers, cyclone performance, and regenerator activity. Erosion-prone components like slide valves and standpipes are instrumented with vibration, wear, and temperature sensors. In some modern units, AI-driven condition monitoring predicts maintenance needs and triggers alerts for mechanical inspections before a failure occurs. Wet gas compressor, WGC control is another vital part of FCC operation. As the primary gas handling equipment for cracked products, the WGC must maintain stable suction pressure and protect downstream recovery units. VFD-controlled compressors or steam turbine governors are managed via anti-surge and load-sharing logic, often coordinated with overhead vapor flow from the main column. These compressors now integrate with unit-wide APCs to adjust for feed swings, hydrogen content variation, or load-shedding events during flare system saturation. Emissions and environmental controls have become deeply embedded into FCC operation. Regenerator flue gas is closely monitored for NOx, CO, and particulate emissions using inline analyzers. Emission control devices such as electrostatic precipitators, ESPs, CO boilers, and selective catalytic reduction SCR systems are managed with feedback from these analyzers. Control logic adjusts combustion air distribution, catalyst additive injection, e.g., NOx reduction additives, and flue gas temperature to maintain emissions within regulated limits while preserving regeneration efficiency. Safety systems are also more intelligent. FCC units involve high temperatures, flammable hydrocarbons, and large inventory flows, making SIS and ESD logic essential. Modern systems use multi-layered logic that stages trips based on severity, e.g. partial catalyst withdrawal, feed cutback, or full depressurization. Pressure relief devices, reactor overtemperature interlocks, regenerator oxygen limits, and catalyst bed level alarms are tied into advanced alarm management systems with prioritization, shelving, and operator guidance protocols. Digital twins of FCC units now simulate entire unit behavior in real time. These models replicate reactor regenerator dynamics, catalyst aging, fractionator vapor liquid loads, and compressor behavior. When linked with historian data, these twins support fault detection, operational forecasting, and what-if scenario planning. For example, an operator can simulate the effect of increasing feed density or decreasing riser steam without disrupting live operation, enabling proactive decision-making. At the enterprise level, FCC units are increasingly optimized not in isolation, but as part of integrated refining platforms. Advanced process control systems consider margin-based targets, e.g. gasoline versus LPG value, hydrogen availability, blending constraints, and coker interactions. AI-driven systems are emerging to predict catalyst decay rates, automatically adjust yield targets, and recommend slide valve set points. In this context, the FCC transforms from a high-risk, high-yield operation into a fully orchestrated, digitally resilient, and self-optimizing production engine, anchoring the economic performance of the entire refinery. Unit operations control, modern crude oil heating column control for thermal conditioning and distillation stability. Crude oil heating columns, also known as pre-flash or preheat columns, are critical in front-end crude distillation units, CDUs, tasked with separating light ends from crude and conditioning the feed thermally before it enters the main atmospheric column. Though simpler in function than full distillation towers, these columns have outsized influence on energy efficiency, product slate distribution, and the operational load on downstream units. Modern control of crude heating columns focuses on dynamic thermal balance, vapor-liquid equilibrium stability, pressure and reflux management, and integration with upstream heat exchanger networks and downstream fractionation strategies. The primary control objective in a crude heating column is to maintain stable overhead vapor recovery and bottom product conditioning under highly variable crude feed conditions. The overhead typically removes lighter components, e.g. C4 naphtha range, while the bottom's flow, preheated but largely unflashed, feeds the main CDU column. The system must maintain optimal top and bottom temperatures, column pressure, and reflux ratio to ensure proper vapor-liquid separation while avoiding off-specification products or operational upsets. Feed variability presents the greatest control challenge. As crude API, light end content, and sulfur levels vary, the pre-flash behavior can shift significantly. Modern units integrate feed characterization sensors or model-based inferential controls that assess naphtha content or light end concentration in real time. These inputs allow dynamic tuning of column top temperature or flash zone pressure, ensuring consistent stripping efficiency regardless of crude slate changes. Advanced process control APC systems often layer on top of base regulatory control to manage the interactions between temperature, pressure, and vapor load. Temperature control in the column is typically achieved through furnace outlet temperature manipulation, guided by feedback from column internal trays or flash zone sensors. Smart temperature profiling with multiple thermocouple levels allows the control system to infer vapor load and entrainment risk, enabling fine-tuned adjustments to heat input. This is especially critical to avoid overflashing, which could overload the pre-flash condenser or send excess light ends into the main tower, disrupting atmospheric distillation equilibrium. Column pressure control is crucial for maintaining the vapor-liquid envelope and ensuring stability in the reflux system. Typically, pressure control valves, PCVs, on the overhead vapor line or vent-to-flare controls are used to maintain column top pressure. In more advanced systems, vapor balancing with downstream gas recovery units or flare header systems is implemented, with APC logic coordinating vent flow to minimize emissions and flaring. High-fidelity pressure control also protects from entrainment of heavier components, which could degrade overhead condensate quality. Reflux control is another key component. Fixed or ratio-based reflux control can result in instability during feed or pressure swings. Modern columns use level-to-reflux cascade control or temperature-compensated reflux ratio adjustments to respond dynamically to load changes. Variable frequency drive VFD driven reflux pumps allow fine control of flow rate without inducing surge conditions. The system monitors overhead condenser duty and adjusts reflux accordingly to maintain internal column hydraulics within stable operating limits. Instrumentation plays a central role in enabling fine-tuned column control. Guided wave radar, GWR, or differential pressure transmitters are used for accurate bottom-level monitoring, while pressure-compensated thermocouples ensure reliable temperature data even under two-phase flow conditions. Inline composition analyzers or naphtha cut point estimators can feed inferential quality control loops that adjust flash conditions based on product blending requirements or downstream unit constraints. The heating column's role in heat integration further enhances its operational complexity. It interacts directly with the crude preheat train, where heat recovery from overhead vapors or bottom stream is used to pre-warm incoming feed. Advanced control strategies synchronize column heat duties with hot oil circulation loops, furnace firing rate, and main CDU heat exchangers to achieve maximum thermal efficiency. APC logic may optimize firing rate, steam stripping, and exchanger bypass based on calculated pinch points or real-time energy KPIs. Safety and reliability are managed via tight integration with safety instrumented systems, SES, and emergency shutdown systems, ESD. Overpressure, high level, and tray flooding detection are implemented with automated protective actions, such as flash gas diversion, heater ramp down, or reflux cutback. Alarm management systems provide operators with prioritized guidance during disturbances, and smart valve diagnostics ensure that control elements respond correctly during transient conditions. Looking ahead, digital twin models of crude heating columns are being deployed in cloud and edge environments. These twins replicate vapor-liquid equilibrium behavior, flashpoint prediction, and energy balances based on real-time sensor inputs and historical data. They enable predictive control, adjusting column set points in advance of expected feed changes or shutdowns. When coupled with AI-based pattern recognition and refinery-wide optimization platforms, the heating column transitions from a passive intermediary to a proactive control node that enhances CDU flexibility, reduces energy intensity, and maintains operational resilience across a wide range of crude blends.